In this video, I'm going to be discussing the structure of benzene. So benzene is made up of 6 carbon atoms in a hexagon structure, and you'll often see it with a circle in the middle, or you'll see it drawn with alternating double and single bonds like this. Now, the 2 structures that I've drawn here are representations of different models of benzene. So we have the delocalized structure here, and we have Kekule's model here. So Kekule was the scientist who came up with this model. But which one is the more accurate picture of what's going on? Well, we can look at various pieces of evidence. So the first of these is the bond lengths. So in Kekule's structure, we'd expect the length of the double bond to be shorter than this single bond. So we'd maybe expect it to look something like this, if I was to draw it in a very exaggerated way. But in actual fact, when you measure the lengths, they are all the same. So this supports the delocalized structure being the correct one. The second piece of evidence we can look at are the enthalpies of hydrogenation. So what do I mean by this? Well, you'll probably have come across the idea that we can have an alkene like ethene, and if we add hydrogen across that double bond, it turns into an alkane. So this is ethane. And similarly, we can take a molecule of cyclohexene, add hydrogen across the double bond to turn it into cyclohexane, and there will be a certain enthalpy change associated with this reaction, in this case minus 120 kilojoules per mole. Now we can imagine if we had a molecule of Kekule's structure of benzene with the 3 double bonds, and we added 3 lots of hydrogen across that to make cyclohexane, then the enthalpy change associated with that would be 3 times what we have up here. So we would expect minus 360 kilojoules per mole. But when you measure this enthalpy change, it turns out to be minus 208 kilojoules per mole. So the fact that these numbers are different suggests that Kekule's structure isn't quite right. But what is going on here? To explain this, we can draw a diagram to show the energies of the various species in this reaction. So up here we're going to have Kekule's structure with an energy there. And then down here we're going to have our cyclohexane that we're converting it into. So this gap here is the minus 360 kilojoules per mole. Now the actual enthalpy change is minus 208. So this must be a shorter arrow than minus 360, and therefore must correspond to a species with a lower energy, i.e. a more stable compound than Kekule's structure. And a structure that is more stable than Kekule's is the delocalized structure. So the difference in energy between the minus 360 and minus 208 represents the difference in stability between Kekule's structure and the delocalized structure. So once again, this supports the delocalized structure. The third and final piece of evidence we can look at is benzene's resistance to react. So you'll probably have come across the idea that you can take an alkene and react it with bromine, where the double bond breaks open and you end up with this product, with the bromine adding across the double bond. And this is a common test for an alkene. It will decolorize the bromine water. But when you react benzene with bromine, it doesn't decolorize the bromine water. You get no reaction happening under normal conditions, and instead you'd actually have to add a catalyst, a halogen carrier like FeBr3, to get this reaction to happen. So again, this shows that benzene is more stable than just a simple double bond. So in summary then, we have three pieces of evidence to support the delocalized structure over Kekule structure. These are the bond lengths, the enthalpy changes of hydrogenation, and benzene's reactivity or lack of reactivity towards bromine. So now we've established that the delocalized structure is the correct one. Let's look at this in a bit more detail. So benzene is a flat molecule. All of the carbon atoms are in the same plane, and each carbon is bonded to two others and a hydrogen. As I expect you know, carbon has 4 electrons in its outer shell. So we've got 2 electrons in the 2s, and here we have the 2p. If each carbon is using 3 electrons to form these 3 sigma bonds, then what happens to this 4th electron? Well, the 4th electron is going to be in a p orbital at right angles to the plane of the ring, like this. And because these p orbitals are all in the same orientation, they can overlap sideways to form a delocalized pi system. So the result of this is that you have a ring of delocalized electrons above and below the plane of the ring. And that's what gives benzene its stability. If you found this video helpful, please like and subscribe. My next video is all about naming compounds of benzene, so check that out. There'll be a link in the description.